Okay, good evening, everyone. So let's get started. So welcome to this lecture, second lecture on in computational methods in engineering. So we kind of just getting started with the Gaussian elimination method. So we said, okay, a Gaussian elimination is basically a formal name that is given to an algorithm that systematically eliminates variables from successive equations. Okay, so we said a general system is essentially A11 x1 plus A12 x2 and so on plus A1n xn equals B1 and A21 x1, A22 x2 and so on, A2n xn equals B2. And so on. If we have n such equations, the last equation is going to read an1 x1, an2 x2, plus and so on, ann xn equals bn. So we have n equations and n unknowns, which are basically x1 to xn that needs to be calculated. Right? How do we go about solving this? In Gaussian elimination, what we do is that essentially you consider, let us say, the first row as something known as a pivot row, and the first element, which is this guy, as the pivot element. Okay, and you are going to using this value of a11 and the other values that are there, which are essentially below that, that is A21, 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 A22, and so on to AN1. We're going to make all the elements below this pivot element to be 0 by using row operations. Okay, and then in the next step, okay, when you try to do row operations, you are essentially modifying this entire row. In which this value becomes 0, and then all other values will become something else. And then you're going to make the second row as the pivot row, and then you're going to take the element, this element as the pivot element, and you make this row as the pivot row, and you're going to make all the elements below that to be 0. Okay, and so on and so forth until you reach to the last but one row, which is n-1th row, in which you have just made you would just make this element 0. Then what you're left with is you're left with only one non-zero quantity, that is ann xn, which is a modified value of ann xn, which will remain. That means you are trying to convert this equation into by removing the dependence of x1 from the second equation, x1 and x2 from the third equation, and so on. And in the nth equation, you will essentially remove the dependence on x1, x2 all the way to xn minus 1. And the last equation is only going to have xn as the only unknown. That means this equation will get modified to, so this ax equal to b that we have written, this is ax equal to b, through successive row operations, it is going to get modified into u x equals G. Okay, so where U is now an upper triangular matrix, because everything that is all the elements that are below the diagonal will be below this diagonal will basically be zeros. Okay, that is what we have transformed it to. So as a result, you will essentially end up with an upper triangular matrix. And then when you do row operations, when you change the coefficients here, you have to apply the same operation to this element that is on the right hand side, that is b1, b2, b3 all the way to bn. because, or B2 to Bn, because otherwise you are changing the equation itself. So you should not do that. So as a result, the row operation that you would apply to the coefficients, you will also apply to the right hand side. That means you will apply to the entire equation. That is, A21x1, A22x2, and so on, A2nxn equals B2. For the entire equation, you would apply the row operation. So that is the idea. Now, once you have obtained this kind of an upper triangular matrix with X dependence and G, you can use backward substitution to calculate the entire X vector. Okay, that means we can first calculate from the last equation, we can calculate what is the value of Xn, right? We can calculate what is the value of Xn, and then we'll go use again a backward substitution, calculate what is Xn minus 1, and so on all the way to we'll calculate X1. So that is the idea. So you have two steps in Gaussian elimination. The first one is the forward elimination, which is forward elimination. By the way, please take notes. Although I will share these lecture notes and the videos, you should take notes so that you can write some important points and it will be useful for you later. Okay. So we're going to use, the first step is the forward elimination. The second one is the backward substitution. Okay. So with that, let us first do an example problem. And then we will come back to the algorithm as such. So let us consider AX equal to B, something like 1, 2, 1, 2, 2, 3, and then -1, -3, 0. Okay. And this is multiplied with 3 unknowns, that is X, Y, Z equals, on the right hand side, we have 0, 3, and 2. Okay. So this is the system that is given to us. So we have, this is A, this is X, this is B. Now we want to apply a Gaussian elimination and then solve for what are the values of X, Y, and Z. Okay, so how do we go about doing this? We will first identify the first row as the pivot row. Let us say this is the pivot row and this is the pivot element. So I want to make the elements below this to be 0. So I want to make this 0 and then this 0. But then when I want to make this to be 0, I have to also modify all the elements in this row, including the right hand side. So what I would do is I would say that I want to write a row operation. So we want to perform row operations. Okay. This is nothing but, let us say, the row 2. If I were to call R1 is this first row, this is row 2, this is row 1, this is row 3. Then R2 goes as R2 minus some multiplication factor M21, let me call it as, because this comes to be the second row and the first columns, M21 times R1. Okay. So I want to perform this operation such that this element becomes 0. So what should be M21 such that this element becomes 0 through this operation? That basically, that is nothing but 2 by 1, right? If I would take M21 equal to 2 by 1, then when I subtract this coefficient divided by this coefficient, that is your M2, that is the multiplier we are calling. Multiplier. Okay. Then when I use that multiplier and multiply with R1 and subtract it from R2, I'm going to make this as 0, right? So that's going to be 2. R2 right now contains 2, and then multiplier is 2 by 1, that is 2 times R1 value is 1. Okay. That basically going to make this element 0. Okay. So that is the multiplier. That means the multiplier is nothing but A21 divided by A11. Okay. So that is the multiplier I have, and I'm going to use the same multiplier for the entire row. Okay, that means entire row I am using R2 minus M21 times R1. But then of course I'm going to use the particular value of R2 when I apply for this row, I'll take 2. When I apply for when this R1 comes, I will take this 2, and then this is going to be 3 and this is going to be 1 for R2 and R1. But M21 is going to be the same 2 value for the entire row. Okay, so before we apply this, it is also a good idea to combine this right hand side vector, RHS vector, and add it as an extra column to the A matrix. Okay, so we would like to write this as, as you probably have learned, this is called an augmented matrix, in which we will write this as 1, 2, 1. Okay, 1, 2, 1, and then 0 is the extra column we have added. This is the right hand side, and then we have 2, 2, 3. 2, 2, 3, and then 3, Okay, this is the right hand side. And we have -1, -3, 0, and right hand side is 2. Okay, so this is going to be 2. Okay, so this is the augmented matrix. So that is the augmented matrix. We know that this is the coefficient on the left, on the 3 rows, and this is the RHS vector. Okay, so then I'll do this operation. R2 goes as R2 minus M21 R1, where my M21, the multiplier is nothing but 2 by 1, that is A21 by A11. Okay, so if that is the case, I can perform this operation. So because I have taken the first row as the pivot row, this row will remain unchanged. So we have 1, 2, 1, 0. And the second row is going to be 2 minus 2 times 1, that is 2, that is equal to 0. Then we have 2 minus 2 times 2, that is 2 minus 4, that is minus 2. Then we have 3 minus 2 times 1, that is 3 minus 2, that is 1. We have 3 minus 2 times 0 is 3. Okay, that is what I have obtained. As you can see, we made the value below A11, below the pivot element, as 0. Now we want to perform similar row operation for the third row as well, such that we're going to make this element also as 0. So for that, I will say that R3 goes as R3 minus M31 times R1. So I should always work with R1 because R1 is my pivot row. Okay, so this is my pivot row, so I should always work with this. Similarly, 1 here, which is A11, is my pivot element. Okay, so then what would be the value of M31? M31 would be equal to this value divided by this value. That is going to be A31 divided by A11. That is nothing but -1 by 1 is what I would use. That is basically -1. Okay, so that means if I perform this operation, that's going to be -1 minus of -1. That's basically going to make it 0, right? Or you can think, yeah, so essentially this is going to be -3 minus of -2, that's going to be +2, that's going to be -1. 0 minus of -1, that's going to basically make it +1. This is going to be 2 minus 0, that is 2. Okay, is this correct? Is everybody able to follow what I'm trying to do here?
Yes, sir.
Okay, fine, good. Any mistakes? If I make any mistakes, please let me know, okay, so that I can correct them right away. Okay, fine. So that is what we have done. Now we have obtained a matrix, which is a transformed matrix. But then after performing row operations by identifying the first row as the pivot row, then we have basically made these two elements 0. Now we want to identify the second row as the pivot row. Okay, so this is going to be the pivot row. Then my operation would be only needs to be done for R3. So R3 goes as R3 minus M32, because my pivot element is now A22. So A22 is the pivot element. Okay. Okay, then R3 minus M32 times R2. So what would be the value of M32? M32 is nothing but A32, that is this value, divided by A22. Okay, that is nothing but -1 divided by -2, that is 1 by 2. Okay, so if I were to apply this operation, then what we're going to get is, again, now because I have chosen the second row as the pivot row, both the first row and the second row remain unchanged. So we are only doing operations for the rows below the pivot row, right? So this is going to be 1, 2, 1, 0. This is going to be, second row is going to be 0, -2, 1, 3. Third row is going to be, this is 0, this is 0, so this will be 0. Then you have -1, minus of -2 times 1/2, that's going to be -1 plus 1, that's going to be 0. This is going to be 1 minus 1 by 2, that's going to be 1 by 2. And this is going to be 2 minus 3 by 2, right? That is going to be, again, 2 minus 3 by 2 is going to be 1 by 2, right? 3 minus 1.5, so that is 1 by 2. Okay, so now, as you can see, we have performed row operations, and then we are done with the forward elimination, right? So we have done with the forward elimination, and we have obtained the matrix in the upper triangular form. Right now, a matrix is in upper triangular form. As you can see, the right-hand side also got modified. So we had something called B before. The B was having values of 0, 3, 2. Now this new B has got values of 0, 3, and 1 by 2. Okay. So from here, now I can put it back in the original form. That was 1, 2, 1, 0, -2, 1, and 0, 0, 1 by 2 times xyz equals, on the right hand side we have 0, 3, 1 by 2. And now we can solve using back substitution. So this is going to be, when I do the back substitution, this is going to be, this is backward substitution. That is going to be 1/2 times z equals 1/2. That means z equals 1. Okay, and then when I multiply this with this, you're going to get 0 times x, that is 0. You have minus 2y plus z equals 3. Okay, substituting z equals 1 is going to give you minus 2 equals 2. That means y equals minus 1. And from the first equation, you have x plus 2y plus z. So that's x plus 2y plus z equals 0, which is going to give you, substituting for z equals 1, y equals minus 1, is going to give you minus 2 plus 1, that is minus 1, which is going to give you x equals 1. Okay, so that means my solution x, y, z for this problem is equal to 1 minus 1, 1. Okay, so that is the solution, and which we have now calculated and obtained it from using Gaussian elimination. Okay, so that is the idea of Gaussian elimination. Now we have to write a general algorithm so that this process can be done for a matrix of any size. For example, this n in this particular case, the A matrix was only a 3 by 3 matrix. There were 3 rows and 3 columns. But then later on, we would like to say apply this algorithm to a much bigger matrix. N could be 10,000 or even larger, something like that. But then, so even if you have, let us say, 10 power 4 by 10 power 4 matrix, we should be able to solve it using, given the computational power, we should be able to solve it using Gaussian elimination. So how do we write an algorithm for that and a program for that eventually? Okay. So before we proceed to write the general equation, any questions on this so far? Any questions, clarifications, mistakes? Or is it all right? Everybody is able to follow? I think probably.
Yes, sir.
Yeah, okay.
Yes, sir.
So shall we? Yeah.
Sir, you are multiplying that R3, that row
R3.
we were eliminating. So that
Correct,
time
correct.
we can also consider this M32 in R3 also, no, sir? Like, for example, I can multiply 2 in the third row and also can consider and make it 0 for making an upper triangular matrix, right?
Say it again. You want to consider instead of R2. So R2 is the pivot row.
I can consider multiplying 2 onto the third row, and also I can.
Yeah. Yes.
Can do,
So,
no, sir?
Yeah. So what you're trying to say is that instead of this multiplier, you can take 1 by that of the multiplier.
For example, if I multiply 2
So instead of
with the third row,
yeah,
and maybe if I subtract R3 and R2, then
sure.
again an upper triangular matrix will be obtained. Will the answer be same?
So okay, what you're telling me is basically R3, you want to make it as 2 times R3,
Yes, sir.
right?
Yes,
2
sir,
times
yes.
R3 and then minus R2. Something like that. You can do that, not a problem. It can be any row operation, doesn't matter.
Okay.
Anything is fine. But then all I'm trying to do is that I want to do it this way, because once you define the multipliers, you don't have to change, you don't have to multiply your this row with any other number. You only have to multiply one row with a number, and then you just have to subtract it from the other row on which you're operating. That's all.
Okay, sir.
See, for example, because as you can see here, this is -2, this is -1. You can say, okay, what I said is you can make this multiply this with half and then subtract it.
Correct, sir.
What you're saying is that instead of that, you want to do 2 times of this and then subtract it. Both are the same. But then when it comes to writing an algorithm, it is easier if you formulate your algorithm such that you will find some multiplier which is this upon this, and then multiply that with this particular row, and then you subtract from this row.
Okay, sir. Okay.
That is easy because that will work for, then you don't have to worry about defining it any other way.
Okay,
but what you explained is also fine. That will also work. But it's just that it is straightforward if you do it this way. So you don't have to worry about pre-multiplying the row on which you're operating.
Okay, sir.
Yeah, that's all. Yeah. Any other questions, anybody?
Sir, in the next step, on the row 3, element 4, that 1 by 2.
Yeah.
So I think there is some computational error.
Is
in
it
the
mistake?
below in the below matrix.
In here, okay. Here in this one.
Yeah, row
okay.
row 3, line column 4.
Row 3, column 4. This one, eh?
Yes.
Okay. 2 minus, oh, I see. This should be with 3, right? 2 minus 3 by 2. That is correct only, no? 1 by 2, right?
Okay, sir.
Yeah, that is
got it.
correct. Yeah. Okay. And any other questions, mistakes? So, okay. Any other questions? Some there were two voices I heard.
Sir, you said about solver, sir, that means it will be easy for the solvers. Solver will understand that easily. Like, is there any predefined algorithm that it is following, or it follows whatever we instruct? So how it is differentiating, sir, that for the solver?
No, can you explain it again? I did not understand the question.
To Prem's question, sir, you said that if we multiply this third row with 2 and then
I see.
yeah.
No, I think it's a matter of convenience. See, I mean, what I'm trying to say is that you could either do M32, or as the other person suggested, you can even take 1 by M32 and then distribute it to this one, right? Both are fine. Yeah, it's a matter of convenience. That's all. So what we want to do is that, see, I mean, if you do it this way, I have to only see, for example, in this case, it turned out to be 1 by 2. For example, instead of that, let us say this is 2 by 1, and there is always 1 somewhere. Let me give an example where M32, let's say, comes out to be 4 by 3, right? In which case, what you should do is you should multiply row 3 with 3, and then row 2 with 4, and then perform the operation, right? Your R3 goes as 3 times R3 minus 4 times R2, something like that, right?
So, like, whatever suits the best for our operation, so that we can choose.
Yeah, you can do. No, but then what I'm trying to say is that I want you to identify just a fraction, which is basically the element that you want to make it 0 below the pivot element, and then divided by the pivot element. That is your fraction. When you do this, you just have to store only one value of this fraction. That's all. But otherwise, you have to store 2 separate values, 3 and 4. Which is not very convenient. We will see why this is convenient, just storing one fraction little later, okay? Little later. But then
number of operations will increase, and then
it will increase. Correct. And you don't have to also increase the storage, because otherwise you have to store 2 different variables, 2 different numbers. You need 2 different variables. Yeah. Any other questions, or shall we proceed? Now, once this is clear, writing the algorithm is very straightforward. This is clear. Okay, shall we proceed? Okay. Okay. So then what we said is we have this. Okay. So we have. We will rewrite this equation A11 x1. That is our square linear system. A11 x1, A12 x2, all the way A1n xn equals B1. Right? Or let me write it slightly differently. Maybe I'll write it in the matrix form. A11, A12, A13. Oh, sorry. Yeah, this is what we are writing. A1n, and then yeah, that's what we have. And then we have A21, A21, A22, A23, all the way to A2n. And then we have AN1, AN2, AN3, all the way to ANN. This is the matrix we have. And then we are multiplying this with this vector, x1, x2, all the way to xn, okay, equals B1, B2, B3, all the way to Bn. Okay, so this is our general system on which we want to apply Gaussian elimination. Now, to begin with, let me call all these numbers. See, I mean, what you notice is that this matrix will will change, right? It will not remain the same. Once we perform operations, this matrix is going to change. So that means I'm starting with A matrix, but then if you want to preserve the A matrix after end of Gaussian elimination, then you should take a copy of A before you start this process. Otherwise, A will get transformed into U. Okay, that we should keep in mind. You know, many a times in your when you write programs that you may be requiring the previous A, which may not be available if you have not taken a copy. So that you should keep in mind. So then I will also write a superscript 1 to indicate that this is the original matrix or original values of that I'm given with. Okay, these are all I'm putting 1 here, just to say that these are all the original values. Now let me do step 1. Okay, so what is the step 1? So step 1 is basically I am defining multipliers, right? I'm defining multipliers. And how many multipliers should I define? I should define as many multipliers as I have below this pivot element, right? I should define so many multipliers, 1 for each row below the pivot row. That means I should define n minus 1 multipliers, okay? So I will say my first multiplier is m21, that is nothing but a21 divided by a11. We know that these are the superscript 1 to indicate that those are the original values I have, okay? So I'll take m21 and I'm going to perform a row operation on this, right? And then this will basically become 0 and all other values are going to be something else, right? Because they will be a22 minus m21 times a12. Similarly, a23 minus m21 times a13 and so on, right? That's what my operation is going to do. Similarly, I will define, once I'm done with this row, this is the second row, I will go and define another multiplier. That multiplier is going to be m31, that is going to be a31 upon a11, right? So that is still, the multiplier is still with respect to the pivot row. Pivot row is my, so this is my pivot row, this is my pivot row, so it is still with that and so on. So I'm going to define so many multipliers, mn1 equals an1 divided by a11, which are all for the first this thing, okay? So that means I essentially defining I1 equals ai1 divided by a11, right? Where my I is going from 2, 3 all the way to n, right? I'm defining so many multipliers. Okay, and then once I perform an operation on this thing, which is basically a, let us say aij, right? For the next step, that is the second step, is going to be aij for the first step minus mi, right? I'm doing it for the 1, right? Which is basically the so mi1 times a1j, right? That's what I'm doing for the 1. So that is basically going to transform my values that I have for in all the rows, right? And then my I and j are going to go from 2, 3 all the way to n, right? Because I'm only going to modify. I know that these values will anyway become 0. These are all going to be 0. So I need to modify this entire range of values, right? Everything that is there. That means my I starts from 2 and my j starts from 2, right? And then 2 to n and 2 to n. So all these values that I have will get changed, and they will get changed according to this equation, right? That is means my aij in the, once it is done with the first step, I'm getting the values for the second step, that is aij2 equals aij1 minus mi1. I'm multiplying this with a1j. A1j is going to be the first row and the corresponding column, right? Either I use 1, 2 or 1, 3 and so on till 1n. Okay, so that is my operation. Is this correct? Any questions on this? Right, I've just written in using these alphabet, you know, the A and M that we have for whatever we have done numerically. Now that means, but then once I do this thing, my matrix A, after I perform this operation, okay, I'm not done actually, because I should do this and I should also modify my right hand side. My right hand is BI2 is going to be BI1 minus MI1 times B1 of 1, right? I have to multiply with use the multiplier, multiply with B1 and then modify all these values, right? That's what I should do. Okay, fine. So once I perform these many operations, my matrix is going to look like A11 A12 all the way to A1n. And these are for values of 1, which are untouched because this is the pivot row. Then I'm going to get 0. This is going to be A22 all the way to A2n. But these are now 2. I'm using subscript 2 denote that the first step is over and we have values for the second step. Similarly, this is 0 all the way to 0. And we're going to get there will be some values here, okay, A322 and so on, AN22 and ANN2, right? So that is what we will have. And on the right hand side, we have, and this is x1, x2, xn. And on the right hand side, we'll have B11, this is untouched. Then B22, B32 all the way to Bn2, right? Everything below B1, which is B2, B3, Bn are all now modified to be ready for the second step. That means this is done after the first step, right? First step is over, so we have new values for B's and all these values, right? These are all new values, right? This entire, if we had a matrix of n by n, this entire n minus 1 by n minus 1 is now new values that we have obtained. Is this clear? This is exactly same as what we have got after the first one, right? So this is so this was the original matrix. Then I have obtained this matrix, right, in which only changes were these were zeros, and then we have modified this entire thing, right? That's what I'm kind of trying to say here. Do you agree what I have written or no? Is it clear, this part? This is for step 1.
Yes, sir. Clear.
Clear, okay. Okay, then I can do, I can essentially do the same thing for step K. That means I have moved from step 1, that is row 1, to step K, right? That means when I have done step 1, 1 is the pivot row. When I do step K, K would be the pivot row. That means I have to define again so many multipliers, and my multipliers would be M. Earlier I had defined my multipliers MI1, right? MI1. Now I'm going to define them as MIK as AIK divided by AKK, right? So earlier I have written MI1 as AI1 divided by A11. Now, instead of doing it for the first row, I'm doing it for the kth row, right? That means I should replace 1 with k. Basically, I have MIK equals AIK by AKK. Of course, these values are not the original values that are given to us. These could have been already modified because of the row operations that were done till k minus 1. So these are going to be AIK K and AKKK, right? These are the values of A matrix at the kth, available for the kth step, okay? So that is, that's what I have for MIK. This is AIK divided by AKK at kth step. Okay, so that's what I have. So that is the multiplier. Of course, my K will run from so this is basically the kth row, right? So that means my I will run from k plus 1 all the way to n, right? Because if I'm doing kth row, I should do these multipliers only for the elements that are below and to the right. So I should run from k plus 1 to n. Okay, so these are the multipliers. I will define so many multipliers. Then I can do my row operations as Aij k plus 1, right? Because now I am updating to the next level equals, I operate on Aij k minus Mik. These are the multipliers. I should multiply them with AKJ, right? I should multiply with, if k were 1, I should multiply with the first row. If k is 2, I should multiply with the second row elements, and j will give me the corresponding column, right? Just like I have done Mi1A1j, I'm doing Mikakj. And of course, these are the available values of k, right? Available values, and then we are modifying the value. Similarly, my B, which is the right-hand side, will get a new value at k plus 1. This is going to be Bik minus Mik and then Bk. I should multiply with the Bk, that is the row pivot element on the right-hand side for that particular Bk, right? And again, we understand that my I and j will both go from k plus 1 all the way to n, right? So whatever ij I have written, they run from k plus 1 to n. That means you go from one row below that, you modify, and then from there you modify to the right-hand side, right? That's what we're doing. That is the, because everything below k will become 0, right? Everything below k will become 0. So from k plus 1 on,